Deepankar Sarmah. So Dr. Sharma is actually from Basel University, Switzerland. He's a specialist in nanofabrication for quantum devices with a strong background in condensed matter physics and quantum technologies. After obtaining the PhD from the University of Basel, Switzerland, his research focused on semiconducting spin qubits and circuit quantum electrodynamics. Currently, he is working as a joint postdoctoral researcher at the University of Basel and a research scientist at YQuantum, a Switzerland-based quantum startup. And he leads the development and fabrication of next-generation quantum hardware, driving innovation towards scalable quantum technologies. The title of his talk is Circuit Quantum Electrodynamics using High-Impedance Resonators and Qubits in Nanowire Quantum Dots. Over to Dr. Deepankar Sarmah.
Thank you so much for your nice introduction, and I'm very honored and happy to present my research in front of all of you. Before I begin, I would like to start with some very basic key terms, which would be very important for the talk that I'm going to deliver today. So I say some basic vocabulary. Nanowires, so it starts with nanowires. So nanowires are one-dimensional structures. So as the name suggests, they're nanometers in dimensions, the diameters, where electrons are only allowed to move in one direction. And now if I further limit the movement of electron and trap it, then it becomes a quantum dot. So, and then there are different electrochemical potential levels of these quantum dots, which can be moved, and well, it kind of mimics an atom. And qubit, you might have already heard about it from all the lectures today. So it's the basic unit of quantum computing. And then the qubit is a bit which can exist in superposition 0 and 1 at the same time. Very important resonator. It traps a photon. Let's say it enters a photon from one side, it traps it, and at certain frequency it oscillates, or the photon can come out of there. So hi, I welcome you all to my talk today. It's called Circuit Quantum Electrodynamics using high-impedance resonators and qubit in nanowire quantum dots. I am an experimentalist, so I'm going to show you some of the research work that I did during my PhD here at the University of Basel. And so it might be a little bit specific to my work, but I'll try to make it, convey the message that I want to in the next 30 minutes or so. So I want to take you a little bit back to motivate why I want to do what I'm doing. If we go like 40 years ago, at MIT, 7th May 1981, Richard Feynman delivers a lecture in this seminar, which was called Physics of Computation. And the title of his talk was Simulating Physics with Computers. In this talk, he says that nature is not classical. So if you really want to understand how nature functions, you should do a quantum mechanical simulation rather than classical simulations, because the nature itself is quantum mechanical. And 40 years later, where do we stand? That's the question. Well, if we look in recent years, there have been a huge interest in the field of quantum computing from all over the world, right? Also recently, India announced the National Quantum Mission with around 6,000 crores of investment. So why? The question is, why is there so much of, interest in quantum computing? Well, theoretically, or at least as of now, the idea is that with quantum computer, it could help us in drug discovery. If we can model the molecular interaction, if you can really see how the molecules can interact with each other by simulating them in a quantum computer, we can skip the long years of trials, clinical trials and whatnot. So drug discovery, material simulations, cryptography, you might have heard just a lecture on quantum cryptography. It's also one of the key area where everyone is interested in. All the countries, US, China, Europe, India, everyone is trying to get in this race of quantum computing, because this is something which will enhance the cryptography and security in everything. Besides this, there are optimization problems like, logistics, supply chain optimization, traffic management, portfolio management, machine learning, and AI. And also, in order to simulate quantum systems, exploring phenomena in condensed matter physics, or studying the origins of the universe, quantum simulation could be a key in that. Well, jumping quickly into my talk today, there are various quantum computing platforms, but I will only show you some things that are related to which I can drive you towards my talk today. So I categorize them into two different sections. One are like natural qubits, for example, ions and atoms. They're available naturally in the nature. We need to take them, then, like for neutral atoms, cool them down to millikelvin, or close to absolute zero, and then try to exploit, or do some kind of operations on them. For ions, we can just take them from nature, and then trap them somehow, and put them in ultra high vacuum chambers, and then do some operations on them. So these are kind of natural qubits, which I categorize them. Then there are other kind of qubits, which are fabricated qubit, which are manufactured qubits in the lab, such as the superconducting qubits, which is one of the most successful, which IBM, IQM, quantum machines. There are different companies who are, Google is also working on these kind of qubits. Then also there is something called spin qubits, semiconductor qubits. Well, all of them have their plus and pros and cons. For example, trapped ions, they're limited because you need 3D traps, and when you want to scale to millions and billions of qubit in future, which you would need to have a practical computer to do something real, it would be difficult. For neutral atoms, you can make arrays of atoms, but in order to tune them individually, that would be a problem. For superconducting qubits, we are still limited by material losses, because you need to really have everything superconducting, and to of course, they're called superconductors, but there's still the materials have the loss, the internal losses, and so many things are a problem. The good thing with spin qubits is that they're CMOS compatible, meaning that the already existing industry, we have been working on semiconductors since years, right? Like since the first transistor, everything is based on semiconductors. Your mobile, your laptop, all the electronics are based on semiconductors. So because of that, if we can really use the already existing semiconductor technology, and then use it to make your qubits, this then would be easier in the terms, right? So I mean, there's this cartoon which says, okay, spin qubits could be the new king of these quantum zoo. Well, so now, just jumping a little bit again onto a little bit further into my topic of interest, resonators, something which is very important, integral part of superconducting, semiconducting qubits. Well, what do resonators do? They are used mainly for two purposes. One of them is to do readout. So whenever you have this resonator, let's say here, if you can see my pointer, I'm not sure. The picture says resonator. When it's coupled to quantum dots, what you can do is, without non-invasive readout, without disturbing the qubit, because the change in the qubit occupation will bring a shift in the frequency or the phase of the resonator, and hence, without demolishing the qubit state, there is an exchange of energy, and then we could read out what's really happening in there. The other significance or use of resonator is to do long range coupling. So they're used as quantum buses. For example, you can see, I mean, in future, let's say this is a plan from Van der Sijpen, who's working in spin qubits. If you have arrays of array of qubit, spaced over the place, when you have like a big chip of quantum chip, let's say quantum processor, you need to pass some information from one group of array to another. And for that, in order to make this long range transfer of quantum information, resonators are the best candidates. Well, now let me put all this thing together. We heard about qubit, we heard about resonator. Now, circuit quantum electrodynamics. We all have heard about cavity quantum electrodynamics, right? Basically, a cavity where there's an atom and a photon trapped, like a single photon trapped inside. So, circuit QED describes the light matter interaction at its most fundamental. So, but here instead of cavity, we have a resonator, which is like this blue, light blue thingy in between. Then on the right hand side, we have the qubit. And then there's the interaction, which is shown by the green arrows. It's just the interaction between the resonator and the qubit. Well, we all might have heard about Jaynes-Cummins Hamiltonian, a very famous Hamiltonian in physics when you talk about light matter interaction. So we can use the same Hamiltonian to also describe circuit QED. So the first part of the Hamiltonian is describing the resonator. A resonator can be understood as an LC oscillator, right? Which oscillates at a frequency omega r, which is the frequency of the resonator. Then the Hamiltonian is then given by h cross omega, a dagger a, which is the number operator, which essentially says how many atoms are trapped inside, how many photons with energy h bar omega are trapped inside the resonator. And then you have this electric field fluctuation, which is described by E. If we look at the other side of the picture, we have the qubit, which is again defined by in a nanowire quantum dot, which we'll look at later. But let's say we have a qubit with two states, ground state and the excited state, h bar omega. The Hamiltonian is given by h bar omega by 2. There's half h cross omega sigma z, which then tells you whether you are on the lower or the upper state. And the dipole moment of this atom is d. Now the interaction term is given by d times E. So the strength of interaction is proportional to the multiplication of the dipole moment times the electric field, which can be written as the formula that you can see there, involving some raising, lowering operators, and G, which is the coupling strength. Well, I say all of this now because I want to focus on G, which is the coupling constant. And we want this G to be larger so that the interaction is better. Larger, how large? It should be much more than the gamma and kappa, where gamma is the decay of the qubit and kappa is the loss in the resonator. So before my qubit is decayed or the resonator photon is lost from the cavity, we should be able to do some operation on this system. So that's why we need G to be much bigger than that. Okay, now let me tell you about the material system that I work with. So there are two different material systems that I in past have been working with. One is indium arsenide crystal phase nanowires and germanium silicon core shell nanowire. Although they're nanowire, they differ a little bit in their structure and how they're grown. Well, one of them, like for germanium silicon core shell nanowire, in the bottom, there is a germanium core where the holes, so it's a hole carrier, and then there's a silicon shell around it, and you need some external gates in order to define quantum dots. So basically the idea is we want to define some quantum dots, and then later we will define qubits in the quantum dots, right? So, and on the top wire system, you see in the indium arsenide nanowire, the barrier, we don't need an external gates to define the barriers, but rather during the growth, when you change the crystal phase of the lattice, going from wood side to zinc blende, there's an offset of 100 millielectron volt, which then acts as a potential barrier, and then you have this isolation where the electrons are trapped, and we have a quantum dot for free. And it gives much more ease in fabrication, like later on. And why do you need spin qubits? Because they're much more smaller as compared to the superconducting qubits. You can do fast gate operations on them, like in a scale of nanoseconds. You can do all electric control, meaning that because of the spin orbit interaction, which is the inherent property of these materials, we could convert the spin to charge conversion. And hence, when you do electrical when you send an electric signal, you can also tune the spin with that. And that's why we need, and this also gives us strong spin photon coupling. Well, very quickly, what kind of qubit we're using. So as I mentioned, quantum dots many times. So let's say this is like a kind of a double quantum dot together. Let's say if you have two quantum dot in a series, so these is the potential that defines the quantum dot like that, and you have two dots, two electrons, for example, it could be holes trapped inside this quantum dot. And now how the charge state looks like is S11 or S20, which is singlet 11 or singlet 20. Well, I mean, I'm not going too much detail into all of these because then it would take like a long amount of time. So I will just, try to not go so much in detail. So S11 means that you have one electron in both the dot. S20 means that you have two electron in one dot and zero electron in one dot, in the other one, right? So it's S11, S20, it looks like this. But once I switch on the coupling, so there could be some tunnel coupling in between these two quantum dots. And when we switch on this coupling, then there is like hybridization of these two states. And then we have S11, S20 hybridized state. So this is the charge states, but we want to have spin qubit. So we want to look at the spin state. So we have spin singlet, and then there are spin triplets states, right? And now this energy diagram, energy level diagram looks a little bit different. Now, if I apply magnetic field, initially there was triplet, which was doing nothing. But now, because of the spin non-zero character, the triplet will start moving with with magnetic field. When I apply a magnetic field, because the spin is non-zero for the triplet, it starts moving. One of them, as you can see here on the right side, that one of the T11 minus goes up, T11 plus starts going down, and then it meets one of the S singlet 20 state. And at some point, again, because of the spin orbit interaction, which I mentioned before, these two states hybridize, and this is the qubit that we want to study, which is a singlet triplet qubit, right? Which is S20T11 plus. I think you cannot see my pointer, but so this is at where you can see there's a delta S0
No,
and
we could see your pointer. Don't worry.
you can see, okay, perfect. So this is exactly here where we define our qubit, and that's the anti-crossing between the qubit, between the singlet and triplet qubit. Well, so this is about the qubit. Now again, why high impedance resonator? So my title says circuit quantum electrodynamics, which I try to explain with high impedance resonator and qubits. Qubit I explained. Now, why high impedance, right? So the resonators, they have impedance. Typically, they're 50 ohm impedance resonator, which are in general, like all the electronics in RF, we try to match them 50 ohm, because if you don't match, there is reflection and so on. So our goal is to have strong photon coupling, right? Strong spin photon coupling. And for that, as I mentioned earlier, this is the conditions that we need to fulfill. Now, the G depends on the electric field of the resonator, which in turn depends on the impedance of the resonator, also frequency and the impedance Z. Now, frequency, we cannot play with it so much because we should be near the frequency of the qubit. So the only thing that we can change is the impedance, and the impedance is given by inductance divided by capacitance. The capacitance is also limited by the geometry. Inductance has two components, geometric and the kinetic inductance. Now, kinetic inductance is again something which is coming because of the resistance of the Cooper pair while moving through the superconductor material. So this itself has a if you want to explain it, it takes some time, but so what is say that the thinner you can make the film, as you can see, A is here, A is in the denominator, the kinetic inductance is higher, which will make the total inductance higher, which will make impedance higher, and we'll have strong coupling. So that's the idea. And for this, we use the material niobium titanium nitride. So that is our material that we worked with. So on top of silicon, we have niobium titanium nitride, where we make our resonators, and then we have indium arsenide nanowires, where we make the qubit. We try to couple them, and then we see what kind of interaction is there. Okay, so today I will talk about, so this was all my motivation and introduction leading to these, leading to the understanding of what I'm going to tell you next. So today I will talk about two small projects from my PhD work. One is about studying the resonator in different dielectric environment, and the second one is the circuit QED with this indium arsenide nanowire and the resonator that we fabricate. Well, so for this purpose, we so we make like 4 different stacks. So idea is we want to see how the quality of these resonators change with different environment, dielectrics environment between, around them. As you can see on the right figure here, so there is a silicon wafer on all of them. So the base is always a silicon. Then there are 2 on the right most where you have thermally grown silicon oxide, right? And then on the leftmost, the niobium titanium nitride is the resonator, like the blue is the resonator. So we have one grown on silicon oxide, then we have grown on silicon but aluminum oxide on top, and then grown on silicon oxide with aluminum oxide on top. So there are the 4 different configurations that we want to look at and see different properties, which will then convince us, can we use certain kind of environment or not? Because why do we do this? So the 4, let's say the stack 4 is in most ideal for qubit integration for the nanowire side, whereas the stack 1 is most ideal for our resonator side. So we want to actually kind of optimize and see which one we can use. Very quickly, we fit the, when we apply a microwave power from one port to measure from the other port, it's called S21 scattering parameter measurement, and we could fit it to obtain frequency, quality factors, and so on. So our requirements are that high impedance resonators, it should be high impedance, it should be high in quality, and it should be magnetic field resilient, because we want to use spin qubits, and spin qubits means we need some kind of magnetic field. And superconductor and magnetic field are kind of enemy with each other, so they don't like to coexist. That's why we want to test how good we are at large magnetic field. For high impedance, we can just use thin film niobium tinitride, as I mentioned before. Problem solved. High quality factor. So we try to then measure this quality factor of all these 4 different stacks. As you can see here in the plot, the number of photons, which is the power. Power can be translated to number of photons. When I say photon, it's microwave photon that I'm talking about. And on the y-axis, we see the internal quality factor. And we see that, okay, the stack 1 has the highest quality, 2 is order of magnitude lower, and the 3 and 4 are a little bit lower. So we saw that when we grow around the oxide, when we have the resonator encapsulated between the oxide, then the quality factor goes down. And it's also understandable because of different 2-level fluctuators which is present in the because of different 2-level fluctuators present in the environment, the loss is higher in that case, and hence the quality factor goes down, right? We also do temperature dependence, so we measure until 50 millikelvin. From 50, we go until 2 millikelvin or so, as you can see here. Similar trend is observed, the highest quality for stack 1, then 2, and 3, 4. Good thing is that we see that all of this, okay, in the previous one, we are more interested in a single photon limit, which is somewhere here. It's a log scale on the X. So the single, because we want to have a photon interacting with a spin. So mostly we will work on the single photon limit, and we see that the quality factor of all of the stakes are more than a few 5,000, let's say. Here we see all of these stacks preserve a quality factor of more than 10,000 or so, which is already good enough. In magnetic field, we can see this is an in-plane magnetic field which is applied parallel to the surface of the resonator, to the resonator plane, and they sufficiently preserve the quality factor well above tens of thousands for all the different stacks. We see a certain dip at around 150 millitesla, and when we try to look at what this is, and when we try to fit it with this equation where omega r is g mu b, which is standard equation, we see that the g factor comes out to be 2, And this is like free electrons. So we attribute this to because of the paramagnetic impurities present in the system. You have a dip, and the similar dip is also observed in case when you apply a perpendicular magnetic field. Well, in plane magnetic field, the resonators are resilient until 5 of Teslas and so on, whereas perpendicular, of course, then it comes really makes this flux vortices, and it's really destroying the superconductivity, but still around until 150, 200 millitesla, the resonator stays well, and the quality factor is more than 1,000. So with this, we conclude that the resonators are high impedance, they're high in quality, and they are magnetic field resilient also. And the overall finding of this project was that all of these stacks preserve sufficiently high quality factor, which is around more than 1,000 for our purpose. So we want to do this circuit QED, right? We want to integrate it with a qubit. And for the circuit QED applications, this number around more than 1,000 is already good. Well, if you go towards the stack 1, it's high quality factor, but if you go towards stack 4, we have the double quantum dot stability, and it also makes the fabrication a bit easier. So keeping this in mind, then we will now take this, we will work on stack number 4, because this then really preserves our double quantum dot. It helps us to increase the coherence, or makes the fabrication process also a little bit simpler. And with this, I will show you the result from the next experiment, where we really try to integrate these two systems together. So here, let me show you. So this is how the device looks like. This thin line here in the middle is the resonator, which is a lambda half resonator again, because it stores a half wave mode. It's not like a full complete wave, but it stores like half wave. And then we have feed line, where input and output to measure S21. Then on the right hand side, if I zoom in, you will see the nanowire with the gates and source, drain, and quantum dots. So now we really kind of integrate the two different systems. One is semiconductor, one is superconductor. So it's like a hybrid system that we are working with. Just an example, I mean, we characterize how the resonator is, we can fit it, and we obtain certain quality factor, and it's all good. Then we do DC characterization to characterize the nanowire. We see this kind of bias triangle, which is kind of a signature of double quantum dot in this system. Then you could take a larger map of these bias triangles, and then we could see this hexagonal honeycomb pattern, which is again a signature of double quantum dot. So we can say yes, that we have double quantum dot system. The quantum dot are kind of coupled to each other, and all good. So this is more like characterizing before we start the real measurement. We could do the same double quantum dot honeycomb measurement with using resonator response. So there are two different measurements actually fundamentally. On the left hand side, we are doing DC electrical measurement. On the right hand side, we are doing RF, radio frequency, like RF measurements. But both of them gives us like exactly same result and same pattern, which validates that, okay, everything is going well with the resonator and the qubit in the nanowire. Then we, with the help of the bias triangle and this, we could extract some, values for lever arm, which then be used to convert the axis. Now we are dealing with voltages, but we can talk about absolute energy scale from these lever arms. Well, now if we go like, in this direction, so what we are looking at right now is called is like where the qubit can live. So this is where interdot transition. So from one dot to other dot, we can move in this direction. So this is kind of interdot transition where we expect our qubit to be. Now, when I move in this direction, what I see, and when I look at the resonator response, I see that there's a shift in the resonator. So now this is no longer a resonator state, but it's kind of a dressed state. So it's a state which is a result of resonator and qubit interaction. Make a line cut, and we could see that, okay, there's a shift in frequency of this dress resonator state. We could fit this, obtain the resonance frequency, the line width, and we could do this for all of the points and then plot it against, detuning. Detuning is again the line that we were crossing through, and then we can fit this to the Jaynes-Cummings model that we saw initially in the introduction. From this, what we can obtain is G, which is what we were looking for, right? We want to obtain the G, which is around 25 megahertz. We will also obtain the tunnel coupling, which tells you the frequency of the qubit, which is around 4.5 gigahertz. So, and then we see that we are in dispersive regime, meaning that we are quite far from the detuning. The G is, yes, different. So now if I increase the magnetic field, because I want to look at the spin qubit, we should see like an anti-crossing. So it's not very clear in this data, but you could see there's some hints of anti-crossing. But we attribute that, because of a little bit poor qubit quality, maybe there's the lead transitions from the nanowire to the source or drain. The transition is very higher, so that the quantum dot is not very isolated, and hence the qubit quality is not so great. We also did two-tone spectroscopy to look at this parabola, which is then described by the charge qubit dispersion relation, from where we could also extract 2T, which is around 8 gigahertz. So the interesting part is that we wanted to do the magnetospectroscopy, which meaning that we go from in this interdot transition, we move along this from one dot to another, and we sweep the magnetic field. Now we saw that there are two different features interesting features that we see. One is the response, as you can see in the first one, is kind of linear at the beginning, and the other one we have a nothing changing, right? And now if we think about it, in the first one, we call this because it's an odd parity, meaning there's an odd number of electron in that system. So now when there's odd number of electron, when you apply a magnetic field, the state starts moving linearly. Similarly, in the other side, we have even parity, and because we have even number of electrons, it most likely, because then at the starting they have like singular triplet character, and then there is no net spin. Net spin is 0. Therefore, the when applying magnetic field, it doesn't change. So this is an interesting thing, because now I want to look at all of these different interdot transition in my whole map, and before that we can start numbering. We can say, okay, we say n plus nm is 0, and from now on we will start numbering. So it's 1 0. When we go up, we add one more electron to the left dot, it becomes 2 0. Go up, 3 0. When you go to the right, you add electron to the right dot. So like that you can map out the whole map. You can see, so 1 1 means 1 1 electron, 2 1 electron. So as you go up with the VR, you add electron on the left dot. As you go with VD, you add electron on the right dot. So now, if I look in all of these interdot transition, let's say for number 1, I expect it to be 1 0 0 1, which means it should be odd. And I see that, okay, it's already dispersing in the beginning, so it's an odd, right? So if I look at the transition number 2, it should be, okay, so it should be an even, because it's kind of 1 1 transition. So at the beginning, it should not disperse, it should be linear. And this is what we observe. Similarly, if I look at 3 and if I look at 4, then this should be again even and odd, right? Let me, okay, now it comes here. So, and what I expect is in the white, and what I get from the experiment is in the green, and it kind of obeys the what I expect from theoretically from mapping out, or writing out this charge states. We did this for all the 16 different maps, and then we found that there's quite an agreement with all of these theoretical predictions. And of course, it is also expected that at some point it will break this agreement, because when you sweep this gate voltage, then there might be some additional orbital which might be introduced, and hence at some point it will break the addition of electron one by one. And this is what we observe also in our experiment. But this is quite a good agreement that until certain number, the addition of electron in this double quantum dot is really happening one by one, right? So this is what we showed in this. Well, to conclude, so I showed you the charge stability diagram, which is like a characterization of the quantum dot or the qubits. I showed you the resonator qubit interaction. Very briefly, I also showed you two-tone spectroscopic measurement, and at the end, I showed you how the double quantum dot shell filling of electron one by one was really happening, and we saw that each of the electrons were filling there one by one. So it went from odd, even, odd, even, odd, even parity. Well, to summarize the whole thing, I showed you two different experiments. The first one where I showed you how the resonators were behaving in different dielectric environment. We have high impedance resonators with high quality factors, magnetic field resilient until few Teslas, in plane, hundreds of millitesla and out of plane. And in the second one, I showed you that we tried to do the circuit quantum electrodynamics with crystal phase indium arsenide nanowires, where I showed you the resonator qubit interaction, followed by some two-tone spectroscopic measurement and also DQD shell filling. So it says that our whole work was to optimize the nanowire resonator hybrid device, because we are dealing with two different things, which is one is superconductor, the whole resonator and the whole ground plane and everything is superconductor, and the qubit is a semiconductor, right? And you need to make an integration between them, which is a little bit tricky. And at the same time, it's a spin qubit, so you have superconductor and you want to use magnetic field, which is also like fighting with each other all the time, because if you apply magnetic field, superconductivity is lost, right? So these kind of hybrid devices needs a lot of tuning and optimization, which was our goal also. And we showed that we also did other experiments and many other different wires and triple dots, and we show that okay, these kind of indium arsenide nanowires are very robust. You could reproduce the results, and they're really useful for such kind of experiment. So with this, I'd like to thank all the peoples that were involved in the project here. And I'd like to thank all of you for listening to me, and thanks to Bhaktivedanta Institute and CDAC for giving me this platform to present my work. Thank you all.